Hello, everyone. My name is Bill. I'm from The Ohio State University, and I'm a Year 3 Economics PhD student. Today, I'm going to make a video about the local average treatment effect. So in this video, I'm going to talk about what is that and why is it useful. So I have posted this set of notes on the description of this video, so you can download it and writing down stuff while watching this video. I find it pretty helpful whenever I write while watching a video. It really helps with my learning, so I hope that can be helpful to you as well. And also, you can ask questions if you have any in the comment section. I will be more than happy to answer them. So without further ado, let's talk about this brilliant idea of local average treatment effect. This is found by two very famous economists, Joshua Angrist and Guido Imbens. So these two economists, many people have told me that these two economists, they won Nobel Prize essentially for this work on reinterpreting what is the treatment effect that we are estimating when the treatment effect is endogenous and we use IV to estimate it. So let's move to the second slide. Before I move into the second slide, I would like to briefly tell you that in short, a local average treatment effect is essentially telling you what is the treatment effect on a very particular subpopulation. And the subpopulation is those whose treatment status actually change while their instrumental variable value change. So in order to understand all these concepts, you do need to know what is an instrument, and you need to know what is endogeneity. So I assume you have this type of knowledge. If you don't, then maybe it's better for you to, then you can, I think you can still watch this video because I will provide some very intuitive examples, and hopefully you can still get something out of this video. So local average treatment effect is for the scenario where you have endogenous treatment, meaning that your treatment actually correlates with error term. So just like any type of endogenous treatment variable actually gives us biased or even inconsistent estimates of treatment effect. So we won't get an accurate estimation of the treatment effect. As economists, one of the very common tool that we use is instrumental variable. So instrumental variable is assumed to not correlate with this endogenous treatment, and we use that to correct the bias. So using IV, in short, we call instrumental variable IV, right? So when we use IV, we can actually correct bias to a large extent, and also we get consistent estimator of for the treatment effect. So throughout this presentation, I'm going to use a very famous example by Angrist. Yes, so Angrist not only found out what is local average treatment effect, he also wrote many very famous, very impactful empirical papers. So in this empirical economics paper, he estimates the impact of joining the Vietnam War Army on the lifetime earning of those soldiers. So so apparently those people who join the army versus those people who don't join the army, they are two different subpopulations, and they are inherently different. So simply differencing their average income will not give us a good estimate of the impact of joining the Vietnam War Army. So we need and also the treatment variable, which is whether you join the army or not, it's gonna be endogenous, because there are so many variables that determines why some person join an army or not, and some of these variables, they are not observable. And unfortunately, these unobservable variables can also have an impact on their lifetime earnings. So there is this endogeneity issue. So we can use instrumental variable in this case. And in his paper, he used the randomly assigned draft number as the instrumental variable. Sorry, I have not been making videos for 2 years, so I'm a little nervous here and I needed some water to calm down. Okay, so let's move on to the theoretical framework. All right. So I'm gonna relate this theoretical framework and all these notations back to the example here, right? The Vietnam War Army example, so that you can better understand what is local average treatment effect. So the outcome variable here is the lifetime earning. So YI denotes lifetime earning of individual I. You can copy it down while watching this video. I believe that will be helpful in terms of you, help you internalizing this concept of local average treatment effect. So the treatment status is whether individual I joins the army or not. Right. And we can actually write yi in this form. Why is that so? So yi is a function of di. So your treatment, so the fact that whether the individual I join army or not, he will have a different lifetime income. So your lifetime income is a function of whether you join army or not. So we can write yi parentheses di to denote that. And this right-hand expression is equivalent to the left-hand side notation. Why? So if di is 1, so meaning that this person, individual I actually joins army, then yi di equals to 1 will give us 1 times yi1 plus 1 minus 1 yi0. And that is exactly yi1, right? And when yi is 0, I think I can leave it as an exercise for yourself. It will be yi0 on the right-hand side as well. So this definition is equivalent. These two definitions, they're equivalent. All right. So the treatment effect here is yi1 minus yi0. So individual's lifetime income when he actually joins army minus the individual I's lifetime income when he doesn't join army. This difference is the treatment effect, and it depends on individual I. So the difficulty in terms of estimating this treatment effect is that these two variables, they are not simultaneously observable. So you can only observe one of them, right? So each individual only lives one life. So it's only possible for you to observe either the lifetime earning of individual I if he joins army, or if he doesn't join army. So if he doesn't join army, so you can only observe one of them. So the difficulty is to actually construct a counterfactual. So if individual I joins army, then the counterfactual would be the lifetime earning of individual I if he doesn't join army. All right. So so we, like I said before, we use instrumental variable in this case to accurately estimate the impact of joining army on the lifetime income. The most important assumption that we make about instrumental variable is that instrumental variable zi, we use zi to denote an IV, is independent from yi0, yi1, and diw. So the first two terms are pretty straightforward, right? So untreated outcome or counterfactual would be independent from zi, meaning that if so zi here is the draft number. Do you remember that? So draft number is actually randomly assigned, meaning that let's say there are two draft numbers out there, 3 and 10. If I get 3, my lifetime earning of not joining army. So since we're talking about untreated here, so if I get a draft number 3, my lifetime income will be the same as as if I get draft number 10, right? So it's independent. My potential, so my potential income, potential lifetime income, when I don't join Army does not depend on that random draft number that government has assigned to me. I think that's pretty fair assumption. And similarly here, we also assume the treated outcome, which is the income, lifetime income if I join Army, would be independent from the random draft number that I get. So again, this seems to be pretty reasonable, right? The third one may be a little hard to understand. It's a little involved, but I will give you a very solid example so as to make sure that you are actually understand it. So let's say we are talking about Vietnam War, right? Draft number. And there are two possibilities. One is 3, the other is 10. All right. So if Bill, which is my name, gets 3 as my draft number, then I choose, sorry, it's a little confusing if I say Bill and then change to I. He will not, okay, will not join Army. If Bill gets 10, he will join Army. Then these two facts, they can never be changed by which number I actually get. So that's what it means by this third assumption where we have DIW being independent from ZI. So what I actually get, which draft number I actually get, does not affect these two facts, all right? So I cannot say that, oh, initially I plan to, if I get 3 and then I will not join Army, but then when I get 3, I was like, oh, I must join Army. No, it doesn't work like that. I have to get this number, this instrumental variable ZI has to be independent from all the possible outcome I get for a given instrumental variable value. So I will write this, not changed by whether, yeah, sorry, it's a little packed here, but I think you can still see it, right? 3 or 10. All right, so with this example, hopefully I've illustrated to you what I mean by instrumental variable is independent from these 3 factors, all right? Okay, let's move on. So with this assumption, actually, we will not be able to identify treatment effect. And I will explain to you why it doesn't make sense to have only this assumption. All right. So usually what we do is to difference. So let's say if we have 2 instrumental variable values, 3 and 10 for the draft number, for example, then we can actually divide our population into 2, right? One gets 3 as draft number, one gets 10 as draft number, and then we average the lifetime income of these 2 groups and then difference them. So this is what we are doing here, right? We can easily write a sample analog of this, which is the lifetime income of those whose draft number is 3 and minus the average lifetime income of those whose draft number is 10, right? And here is a little bit of math. So from here to here, we are essentially just using the definition here, all right? The definition of yi. So left-hand side and right-hand side, they are equal to each other, right? If you sub in that definition of yi, you will get this, all right? And you will see that okay, so I prepared a little some notes here and to help me explain, because the math is not that straightforward. So you will see that these 2 terms, we can write it as DIZ minus DIW. So DIZ and DIW are the treatment status of individual I given their instrumental variable being 3 or 10, or I denote as Z and W here, because Z and W are more general than 3 and 10, right? But if you find Z and W a little hard to follow, then you can just imagine it's 3 and 10. All right. Okay, multiply yi1 minus diw minus diz multiply yi0. And why can I write that? It's exactly because we have assumed zi, right? Which instrumental variable value you actually get is independent from all these yi0, yi1, and diw. So we can write this. We can just ignore the conditional term, because the conditional term is exactly the information of which IV value that you get. Okay, so from this expression, we can actually arrive at here, because it's just factorization, pretty easy. All right, so you see that this is the negative of this, right? So you can actually factorize out that term and then difference these two terms. So you will arrive at here. All right. And it's very tempting for us to just factorize these two, compute the expectation of this and the expectation of that and multiply them together. That doesn't make sense, because we know that the problem we are solving here is endogenous treatment. So DI actually correlate with YI in a way that is through the error term as well. So we cannot do that. All right, so we don't do that, and we see so DI and YI, they are not independent from each other. So we cannot just separate the expectation terms. Instead, we consider two scenarios where DIZ minus DIW is 1 or DIZ minus DIW is 0. All right. So because if if DIZ and DIW, they are equal to each other, meaning that if you minus them and you get 0, then the treatment status is the same, right? So if the treatment status is the same, then there's no difference in the treatment effect. So you cannot actually estimate treatment effect from that individual I, right? For example, if I'm very patriotic, whether I get 3 or 10, I will always join the army. There's no way for you to know the treatment effect of my lifetime income, right? Because I will always join the army. All right. So if we are in this scenario, then DIZ must be 1, DIW must be 0. If we are in the second scenario here, then DIZ must be 0, DIW must be 1. All right. And we can already see this is not a reasonable, it's not a reasonable way to compute treatment effect, because you see that if this is positive, meaning that if lifetime income of joining army, if joining army always have a positive impact on, if joining army always have a positive impact on lifetime income, we actually have a negative sign here, right? So it just doesn't make sense, because we are supposed to get positive estimate. However, when we have a negative sign here, it's possible that this entire expression will be negative, but we know that we are supposed to get positive outcomes. So it just doesn't make sense. All right. So in order to have some meaningful interpretation of this difference, and then link this difference to treatment effect, we actually need to impose even stronger assumptions. And I will show you what assumptions are we making here. So one possible assumption is to assume constant treatment effect for every single individual I. And that is that's a very, very strong assumption. But before me telling you why is it a very, very strong assumption, let me show you why that gives us a a meaningful interpretation of ATE, which stands for average treatment effect. All right. So as you can see here, all right. So this difference, this difference actually is equivalent to this expectation here, right? So if we assume that, so sorry, well, that's not assumption. So we have arrived that the difference between the average income of these two groups is equivalent to this expectation. And if we assume yi1 and yi0 has a constant difference, which is what we are assuming, right? We're assuming constant average constant treatment effect for every single individual. Then this is a constant. So we can write that expectation. Okay, let me copy that down. Yi given zi equals to small z minus expectation of yi given zi equals to w is expectation of diz minus diw multiply a constant term. And the constant term alpha is the constant treatment effect. All right, if it's a constant, then we know that we can write the difference between the expectations of yi given z equals to small z or small w divided by the expectation of diz minus expectation of diw. All right, so what does this mean? Well, you see that here, this is the expectation, this is the expected lifetime income for individual I when his draft number is, let's say, 3, all right? If that is 3, then it's the draft number, 3. If here, this is the expected lifetime income for individual I when he gets draft number 10, right? So the difference here, we know, we can actually compute the average for these two groups pretty easily, right? So we can get sample analog of this and this pretty easily, then we difference their sample analogs. So the sample analog will be what? So it will be the average lifetime income for those who actually get draft number 3. And here is the average lifetime income for those people who get draft number 10. And here, this expectation is the percentage of people who actually get draft number 3. Here, this expression, the second expectation in the denominator is the percentage of people who get draft number 10. So all these numbers, we can actually find their sample analog pretty easily. So we will be able to estimate the constant treatment effect. And since we assume the treatment effect is the same for every single individual, we can actually compute alpha for every single one. However, this is obviously not reasonable. For example, if you have individual I and J, if you have, let's say, Bill and Jonathan, and Bill doesn't have a job, but Jonathan has a job, which is what's happening right now, right? Because Bill is doing a PhD. He doesn't really have a real job now. So, so if Bill doesn't have a job and he goes to army versus Jonathan, who actually has a job and goes to the army, then obviously it's gonna benefit Bill a little more because Bill doesn't have a job anyways. So if he goes to the army, then he gets to pay a little more. So it's still better than being jobless, right? And versus Jonathan, maybe Jonathan has a booming career. He is really, really successful in business. However, in order to go to the army, that if he goes to the army, then his business has to be stopped, he has to, yeah, then obviously it's gonna have a negative impact on his lifetime career. So it's just not fair for us to assume that this treatment effect is actually constant for every single individual. All right. So if we cannot make this constant treatment effect estimation, then what can we do? Maybe we can assume, so Another way to, another assumption that we can make is the probability of certain group of people being zero, meaning that, for example, so we have to assume that for a particular instrumental variable value, so for example, for draft number 3, 0 people will go to the army. So for example, if at that point of time, the president actually announced that those people who get draft number 3 cannot be enlisted. You will never be able to join the army. Maybe for some reason, like you have to keep some man in this country. Maybe it's reasonable. Maybe it's too misogynist to do that. But anyways, so let's make that assumption. If we make that assumption, then you will see that we can actually get something out of this estimation process. So, okay, so let me erase the highlighter. You see that if we assume, let's say DIW, so maybe DIZ, since I said that Z is 3, right? Okay, DIZ, which is DIZ, DI3, 3 stands for the draft number, is actually 0. Then you see that this scenario is actually impossible to, this scenario is impossible to happen, right? So we can actually just erase this part and leave, and we are left with only this, all right? So from there, we can actually interpret something. So let me write down what I have written there. So again, it's the difference between these two, which is the expected lifetime income when Z equals to small z, or versus the lifetime income when the expected lifetime income when Z equals to small I, and that will be equal to let me see. Okay, it's a little messy. Okay, maybe let's still do this. Let's still do Z, this one, okay? DIW being the one with always 0 treatment, always being the control group, always being untreated, always never join the army. Then we can eliminate the second term. Maybe that's easier. I mean, that's definitely easier for me. So probability of DI Z being 1 times probability expectation of yi 1 minus yi 0, given, since DIW is always 0, we can just eliminate this term. So it's DI Z equals to 1. All right. Again, we see that this, we can find a sample analog. This one, I can find a sample analog, right? As we have done it previously. And we can actually compute this, because that's the percentage of people who get a draft number 3, right? So we will be able to compute this treatment effect. And what is this treatment effect? Is the average treatment effect on the treated, right? Because that's everybody who gets draft number 3 and choose to go to, and their treatment status is 1, meaning that this individual I gets a draft number 3 and he actually joined the army, right? Because DIZ is 1. So average treatment, so this average treatment effect on the treated is exactly what I wrote here as ATT. So now we see that if we make these two different assumptions, we can actually get two different interpretation of the treatment effect that we get. All right. However, not necessarily we will always get this nice assumption that DIW, there will be a subgroup whose instrumental instrumental variable value being W and always have a treatment status being 0, always being untreated or never join the army, right? We cannot guarantee that for any draft number that you so we cannot guarantee that there is a draft number such that everybody who got that, who randomly get assigned that draft number will never join the army. We cannot guarantee that, right? Because there will always be patriotic people out there who will join the army. And obviously, I'm thankful for all the soldiers who are out there fighting for the safety of the land that I'm living in. All right. Okay, so enough digression. Let's move on. So those two are assumptions that we make, but they may not be reasonable. So here is another assumption that we can make, which is proposed by Joshua Enquist and Whittle Imbens. And this assumption may be pretty applicable to the example that I'm giving right now. We call it the monotonicity assumption. So what is monotonicity assumption? Well, so monotonicity assumption talks about means that for any instrumental variable value that you get. So in our example, you can only get 3 or 10, right? Then either we have DIZ being greater or equal to DIW for every single I, for every single individual, or DIZ smaller or equal to DIW for every single individual I. So what do I mean by that? So for example, again, we are talking about Bill and Jonathan. If Bill gets 3 and he will join the army, and gets 10, he will never join the army, we cannot have Jonathan gets 3 and then he will not join the army, and gets 10, he will join the army. Meaning that we cannot have this complete opposite decision made by these two men. All right, Jonathan and Bill, their decisions cannot be completely opposite of each other. That's what is essentially written in this math. All right. In a binary case, we can just understand it that way, and that has to hold for every single individual. So, however, this seems to be quite reasonable, right? So if you get, because the mechanism is that if you get draft number 3, then there's a percentage probability of you being induction, meaning that you have to join the army, right? The government actually choose you, such that randomly choose you, and among this group who get this particular draft number, and then you have to go to the army, versus someone else who get a different number, and he will have a different probability of being chosen to join the army. Because of that, at that point of time, actually, when people are called to fight in Vietnam, men actually have different behaviors. So some of them, they choose to join the army voluntarily to, because if you are forced to join the army, then I think your compensation will not be as good. Your condition will be not as favorable. So some people, they actually choose to join the army because they get a bad draft number, right? Bad draft number, meaning that they have higher probability being forced to join the army. So if that's the case, then people's decision will be pretty unanimous, right? So if you join an army so if your draft number is actually not that bad, right? It's pretty good. You don't have much chance of being induction into the army, then you have less incentive to enlist yourself, to volunteer yourself to join the army. However, if your number is bad, meaning that you have a high probability of being being forced to join the army, then you will have more willingness, I guess, to join the army. So people's decision we can pretty much assume that men at that point of time, their decisions are pretty similar to each other, right? So if they join, you know what I mean? Yeah, I have to assume that everybody knows, because I don't think I can explain it in greater detail, but if you have questions, let me know. I think sometimes it's easier if you have particular question, then I can explain it to you. But anyways, monotonicity assumption actually holds in the example that I gave. All right, so if we assume that, remember here, diz has to be 1, diw has to be 0, here diz has to be 0, here diw has to be 1. So you see that only one of this can hold true, right? And it holds true for every single individual, all right? So because diw minus if for individual j is for Bill, diz minus diw is 1, then for every single individual, diz minus diw cannot be -1, all right? Because if that happens, it violates this monotonicity assumption. So we can safely eliminate one of them. So for example, if we know that diz must be greater or equals to diw, then we can safely eliminate this term, right? And then we will get, and then we can actually estimate this expectation, right? And what is this expectation? We call it local average treatment effect. Remember what I said about local average treatment effect? It means the treatment effect on those whose participation status is induced by a change in the instrument. As you can see, diz minus diw is 1. Sorry, is 1. What does that mean? It means that if I get draft number 3, I will join army. If I get draft number 10, I will not join the army. Meaning that if my instrumental variable changed from 3 to 10, my treatment status actually changed as well. So we are only estimating treatment effect for this very particular subgroup. So I have to repeat this point. So if your treatment value if your instrumental variable value change, so in this case from 3 to 10, then you will, at first, if you get 3, you join the army. At 10, you don't join the army. That means your treatment status actually changed from 1 to 0, right? So we are only estimating treatment effect for this very particular subpopulation. All right, so for the next part, which is the extension to the multi-valued instrument, I will make it in a separate video, but the idea is pretty much the same as binary instrumental variable as I have presented throughout this presentation just now. So have fun learning. Remember to subscribe to my channel and like this video. I hope it's very helpful. If it's not, if I still have questions, please let me know. You can always ask me questions in the comment section. I see you guys next time.